Okay, so this is my first video on A-level maths, and I thought I'd cover something pretty fundamental, which is differentiation. There's a lot of videos out there on differentiation, but what I wanted to do here is give you a sort of ascending tier list of questions, where the first one just reminds you of the basic laws for differentiation, and then we move on to something quite advanced in the last one, which shows you where differentiation is leading to and its actual applications in a more general university style context. So I'll put timestamps here of the different questions. Feel free to skip over the first one or two if you're already quite comfortable with differentiation, or speed it up, slow it down, however you want, and I hope it's helpful. Okay, so for this first question, we're given a function f of x equals x squared plus x. We just want to find the derivative of it. So what we're trying to find is df over dx equals what? So the normal rule for differentiation. So we can use the normal rule for differentiation, which is that d by dx of x to some power n, it can be any number, equals bring down the power n times x and then take one off the power. dx of x to the n is n times x to the n minus 1. And we can split this one up. So we have df over dx equals d by dx of x squared plus d by dx of x. And that can be written as x to the 1, just to make this a bit more intuitive. So here we have n equals 2, and here we have n equals 1, if we're going with this form here. So let's just bring these down. So we have 2 times x to the 2 minus 1, of course that's just 1, plus, bring down the 1 times x to the 0. We need to remember that any number to the power of 0 is just 1. So we're left with df by dx is 2x plus 1. Now, let's think about this more in depth. So what's really going on here? Let's draw a sketch of what this function f of x might look like against x. We can do this on any online graph calculator, and it turns out that it looks something like this, where it crosses the x-axis at 0 and here at minus 1. Now what does that mean? Well, let's take the point at x equals 0. At x equals 0 we have df by dx equals 2 times 0 plus 1, which of course is just 1. Now, what the derivative really means is if we take a line that's tangent to the graph f at our point 0, because that's what we chose, then this line here has got a gradient. And the gradient is nothing other than how much the line goes up divided by how much it goes along. So let's call this how much it goes along amount by dx. Let's call this up amount delta y. So the gradient, which is constant for this straight line, is delta y by delta x. And at the point 0, we can say this is dy by dx at x equals 0, where we've just replaced f with a function y. So this can be written f or y, however you like to look at it. And we said that this was 1. So for every 1 unit we go along in the x direction, we go up 1 unit in the y direction. So we can rewrite this as delta y equals 1 times delta x, which might make it a bit more intuitive. So for question 2, we're going to be slightly more advanced, and we're given that f of x equals sine of x over the square root of x, and we just need to find the derivative of f with respect to x. Now, you might recognise this as something where we can use the quotient rule, which is just a rule for fractions, where derivative of some function f of x, this could be any function, doesn't have to be the one we have here, divided by another function g of x, is equal to f prime of x times g of x minus g prime of x times f of x, all divided by g of x all squared, where, for instance, f prime equals df over dx. So that's just saying that the prime notates a derivative. So in this case, we want to know what our function f is and what our function g is. Let's say that our function f is sine of x, because that's on top, and it makes sense. And then that our function g of x is square root of x. And this can be rewritten as x to the power of a half, as you probably know. So, using our rules for differentiation of trigonometry, we have that f prime of x is simply cos of x. That's just a rule that you should know. And then g prime of x, we can use the rule from the first question, just the normal differential rule, which is bring down the power, take one off. So half times x to the minus half, because half minus 1 is minus half. And then this can be written as 1 over 2 root x using indices rules, or however you like. I'm going to keep it like this one for now. So overall, we have that d by dx of sine of x over root x, which is what we're asked to find, is f prime of x, which is cos x, times g of x, which is square root of x, there's a times there, minus g prime of x, which is 1 over 2 root x, times f of x, which is sine x, all over g of x, root x, squared. And root of something squared is just itself, so this can be written as root x times cos x minus 1 over 2 root x sine x all over x. And that's the answer. You can rewrite this however you want. You can times through by root x or whatever you want to do. Okay, so for part B of this question, we have the null function f of x equals sine 3x all squared, and again we want to find its derivative. This time we can use the chain rule because we have a function of another function. We have the squared function of sine of 3x, and that is given by derivative of a function x of another function g of x equals df over dg of x, and this is of x of course as well, times dg of x over dx. And for now we can think of this as this cancels with this. Explicitly it's not, but a lot of people will tell you that this is not just simply cancelling dg of x's, but for now let's think of it like that. So here let's let our function g of x equals sine of 3x, because we have the function f, which is the squared function of sine 3x, and clearly we want the derivative of this g of x with respect to x, so we want dg by dx. Now again, this is a function sine of another function 3x. We can apply this again. I'm not going to do it explicitly because I want you to think about how we can apply this chain rule pretty simply to this function and find that the derivative is cos of 3x times 3. Thinking about it, that just comes from derivative of 3x with respect to x is just 3, and the derivative of sine is cos. So we have that this is 3 cos 3x. Now, putting this together, we have that d by dx of f of x, which is the same thing as d by dx of sine 3x all squared, is given by, well, the squared function just brings down the power minus 1, so 2 times sine 3x all to the 1, because we're treating this function g as a new variable. We're treating it so we just differentiate as if it was an x or a y or anything we want. Then we times by dg by dx, but we saw that that was 3 cos x. So we've got 3 cos 3x. And overall, that gives us 6 sine 3x times cos 3x. And you can use half angle formula, double angle formula. You can play around with how you express this, but this is the explicit answer that we were looking for. So for the third question, slightly more advanced, we are looking at something that might appear in the middle towards the end of a A-level maths paper. We're given a function f of x equals x squared e to the minus 3x squared. And for the first bit, we're just asked to find the x coordinates of any stationary points, which is what we've been doing essentially. For the second part, we're asked which of these is stable. And here some physics comes in, and I'll explain what this means later. If you're not taking any physics courses, then you completely ignore this second part. So, the first part, we want df by dx. Whenever stationary points are mentioned, we are talking about derivatives. So, we can use the chain rule for this like we did in the previous question. So we have this is equal to d of f by let's say that our new function is x squared, so dx squared. If we write it explicitly, then dx squared over dx. But now we have another function, e to the minus 3x squared, so we can do that once more. df by d of e to the minus 3x squared times d of e to the minus 3x squared all over dx. And this is essentially what we were doing before with the g of x function, but writing it explicitly so you can see what's going on. Now, the derivative of f with respect to x squared, that just treats this x squared as a new variable and leaves us with the minus 3x squared exponential term. So that's just e to the minus 3x squared, and then derivative of x squared with respect to x, as we saw in the first question, this is just 2 times x. Then, again, treating this e to the minus 3x squared exponential term, we have that this is a new variable and we're left with x squared, so plus x squared. And then we have the derivative of this exponential term. Well, we know the derivative of e to the x is just itself, e to the x. That's the definition of an exponential function. So here, we're going to use the chain rule. Again, I'm not going to do it explicitly because I want you to think about how we can use this. We treat minus 3x squared as a new g of x function and the exponential as our f function, the outer function, and apply the chain rule. And this gives us minus 6x coming from this term, and then times e to the minus 3x squared. You can think of this by differentiating the term that the exponential is to the power of, timing it by, and leaving the exponential unchanged. So we're left with e to the minus 3x squared. We can bring that out the front, so bracket 2x, then minus 6x cubed. Now we can bring some more things out. We can bring a 2x out, for instance. Then we have 2x e to the minus 3x squared, then 1 minus, got a 2x out here, so we're left with a 3, then an x squared. Now, for a stationary point, that's a definition where this is 0. So, one case where this is 0 is clearly where this x is 0. So we can say x equals 0 is one solution. We also know that it is 0 when this thing in the brackets is 0. So 1 minus 3x squared equals 0. And we can rearrange this, so we get 1 equals 3x squared, then we get x squared equals 1 over 3. Then taking the square root and remembering that we get a plus and a minus, we find that two more solutions are plus or minus 1 over square root of 3. Now, you might be wondering why we didn't equate this term to 0. If you plot it, you'll see that this exponential term never actually reaches 0. It just really, really slowly tends towards it. Okay, so now we come on to the physicsy part of the question. We're asked which of these points we've found is stable. So to think about this, let's plot some examples of functions we might find. We might have a function that looks something like x squared, symmetric, has a minimum. Or we might have a function that is the inverse of this, so for instance, like a hill. Now, if you place an object, for instance a ball, in this function, and then if we had gravity acting down this way, we'd clearly have the ball rolling down and coming to a stop at the bottom of this well, and it would stay within this well. If we had gravity acting down here again, we'd place the ball at the top, and slight deviation from its position would mean it falls down and never returns up to the top. This is essentially what potentials are. If a potential is stable and you put something in it, then it remains within that potential well, and gravity is just a nice example. Now you might recognize these as minima and maxima, and that's exactly what they are. So if we have a minimum of a potential, then we have a stable potential because the ball is going to stay within it. If we have a maximum, then the ball will roll off and it's unstable. So essentially we just want to find which of the points we found was a minimum. So for that, we just want the second derivative. So d2f over dx squared equals what? Well, that's just d by dx of df by dx. That's just rewriting the same thing. So d by dx of that thing we found in the first part, which was e to the minus 3x squared all times 2x minus 6x cubed. Here we can use the chain rule again, differentiating this term and leaving this term unchanged, plus this term differentiated times this term unchanged. That's what the chain rule really is. So let's do that. We have derivative of this term, which we said was minus 6x all times e to the minus 3x squared 2x minus 6x cubed. That's our first term, just concentrating on this bit. Now we come to the second part. We have this exponential term unchanged, and we concentrate on this term in the brackets. So we get 2 minus 18x squared. And that is our second derivative of f. You can rewrite this if you want. I'm going to leave it like this, because it's going to be simple to put in our numbers from the first part. Let's concentrate first on the x equals 0 solution. Here we have d2f by dx squared equals, we get a 0 here, so this term is 0, we get a 0 here, so we're just left with 2 e to the minus 3 times 0 squared. Of course, this is just 0, e to the 0 is 1, and we're left with 2. This is greater than 0. Now, as you probably know, if a second derivative, d2, say f, of dx squared, if that's greater than 0, we're talking about a minimum. So we say this is a minimum, like in this plot we have here. Now, let's concentrate on the next two terms. We had plus or minus 1 over square root of 3. Now, putting in the numbers, you can just do this on a calculator, and we're left with minus 1.47. This is clearly less than 0, and in this case, the opposite of this applies, and we have a maximum. And these correspond exactly to these two cases here. If we zoom in really close to these 2 points, they have this form and this form. We said that our first form was stable, so this minimum at x equals 0 is a stable point, and our ball will stay within it. So I just thought I'd show you what this graph actually looks like with the 3 different turning points. I've plotted x squared e to the minus 3x squared, which is our f, and clearly we have a minimum at 0, as we found, and 2 maximum, one at minus 1 over root 3, one at plus 1 over root 3. This is just 0.577 plus or minus. And clearly we can see that the middle one is a minimum, and therefore if we place the ball along this potential, it would stay within this one. If we placed the ball at the 2 other locations, it would roll off, therefore unstable. Okay, so for this last question, I want to quickly go through an example where we have a function of 2 variables, which means we're working in 2 dimensions for x and y, and the f is our 3rd dimension. So we think of it like this. We have 3 axes. The f function of x and y is on what we call the z-axis, and we have x and y axes. Now f depends on the values of x and y. So we choose a y, and we choose an x, say here, and the function f would have some value. If we move in either direction, x or y, this function value would change. So we get a 3-dimensional surface. Now, to find the minimum of this surface, it's exactly the same as what we were doing, but now we need to do it twice because we have 2 variables. Before, we had df by dx, say, and we'd say that that was 2x over 12. But we're left with this y term. We're not quite sure what to do with that yet. So, what we actually do is replace these d's with curly d's. That might seem like it's doing nothing at the moment, but in our heads, this changes the derivative to a partial derivative, which means we would treat anything that isn't x as a constant, in this case y. So we treat y as just a number. Therefore we have 2x over 12, as we would do normally for the x derivative, plus 0, because the derivative of a number is just 0, and we're treating y as a number. Now, we have the same thing for y. This time we're treating x as a constant, because we're only concentrating on the y derivative, and we're left with 2y over 6. Then, of course, plus 0 for this x term. Now, as before, the stationary point occurs when both of these equal 0. My curly brackets are terrible. So, when does this occur? Clearly, it's when x equals y equals 0. And that is the only time it occurs. Think about it. We have x over 6 and y over 3. The only time those two are 0 is when these x and y are 0 themselves. So we have the stationary point occurs here. There's only one of them, and we're asked to find the minimum in the question. This is a good example where you can use the wording of the question to save yourself doing work. We don't need to show that it's the minimum, because there's only one stationary point, and we're told in the question that it must be a minimum. I just thought I'd show you the 3D plot of our function f here as well. So we have an x-axis, an f-axis, and a y-axis. And the function is a function of these two x and y variables and therefore depends on both of them. We have a minimum at this 0 point here.